Today I am going to present PPT presentations on the topic of performance analysis of a low power, high speed, hybrid single bit full adder circuits for the course completions of digital VLSI circuits. Over the years, increased uses of battery operated portable devices like cellular phones, personal digital assistants, notebooks that demands very large scale integrated circuits and ultra large scale integrated circuits with good power and delay characteristics. In these circuits, single bit full adder is fundamental building block. So researchers have a focus on designing, developing the single bit full adders. And the designing is classified into two categories broadly. One is static styles and another one is dynamic style. In static styles, it is much more reliable, simpler, and less power requirement is there, but it has some drawback also. On-chip area requirement is larger compared to other logic styles, whereas dynamic styles have overall performance is very good, and I'm going to discuss the different dynamic logic styles on the next slide. So there are many dynamic logic styles are there. I'm just explaining 4 or 5 cases here. So first of all, standard static CMOS. So it's basically consists of 28 transistors. The advantage of using static standard CMOS is that it has a good voltage scaling and transistor sizing, and the drawback is high input capacitances and sometimes the requirements of buffers. Whereas the dynamic CMOS, it is also uses 20 transistors, kind of same advantages like voltage scaling and transistor sizing, but it has some drawbacks like path delay and propagations delay reduces little bit of, but not too much. So another one example of dynamic logic style is complementary pass transistor logic. So here transistor count is increases almost 32, but here we can see good voltage swing, but it has some drawbacks like high switching activity, high transistor count. It is behave like a static inverters, overloading of inputs, and voltage degradations problem is also shown here. So we can explain another dynamic logic styles, that is TAG, transmissions gate full adder. Here the transistor count is kind of reduces, like 20 transistor we are using here, and here also the problem of complementary pass transistor logic, the main problem, that is voltage degradations, was completely removed here, but it has also some problems, high input capacitances, and require some buffers. So overall, in this paper, the authors focus on hybrid logic styles, where basically it exploit the characteristics and the performance of the different dynamic logic styles and give a better performance here. But it has also some drawback like decreased speed. But one good advantage of hybrid logic style is that transistor count is reduces. It's almost 14. When we are applying hybrid logic styles, it gives a promising performance, but most of these hybrid logic adders suffer from poor capability issues. But when we are applying in a cascaded mode, if you not put any buffers in the input side or in the output side, then there will be a problem. The objective of this paper is that to improve the performance of parameters like power, delay, and sizing, I mean area. So when the authors compare with the others logic styles and compare with the proper circuit, we got the results, these results. So the design approach of the proposed full order is classified into three modules like module 1, module 2, and module 3, and it has some different outcomes. Like we're using XNOR module, that is module 1, and module 2. So both combine of the both this XNOR module, we're getting sum functions, and then we're applying getting C out functions. So in XNOR module, the first one, that is MP1 and MN1, here basically we are using weak inverters, and MP2 and MN2 also the same. These are the weak inverters. And MP3 and MN3, here we basically restore the full swing output signal. Carry generations modules, here we use strong transmission gates like MP7, MN7, MP8, MN8. So combine of three modules were propose this circuit. The XNOR module, so these portions generates B, these portions generates A, and here basically we are reducing the voltage degradations problem. Whereas MP6, MN6, MP4, MN4, MP5, MN6, combining of these things will realize the complete sum function. If external modules output A and B is same, then we will get C out from this. If it is not same, then we will get C out from the C in module.
Hello, I am Sayandeep-kgpian and I am continuing from this the simulation test bench setup. So in the simulation test bench setup, which we can see that the buffers are added in input stage and output stage, and there are three adder cell stage are there. Actually, buffers are added to minimize the propagational delay, the best propagational delay in the worst propagational delay case. Actually minimize the worst propagational delay, we have used the buffer. The inputs to the adder cells are fed through the buffers to incorporate the effect of input capacitance, and outputs are also loaded with buffers to ensure the proper loading condition. The common prototype of 3 buffers at the input and 2 buffers at the output, the carry propagation and delay from the input to the output started rising significantly in the order of 2 after the first stage. The numerous random signals patterns were applied at the inputs, and the worst case simulation results of the second full adder cell was accounted for analysis. So we are going to the next slide, which we are going to discuss about the performance analysis of this proposed full adder. There is the two tables in the left and right side, we can see. And the left side we are just focusing on the sizing of the transistor which we have used in our proposed full adder, in actually the proposed full adder of this review paper. And the right side, actually the performance analysis by measuring the some performance parameters. And in the left side table, the we actually reviewing the two process technology, that is 180 nanometer technology and 90 nanometer technology, and the transistor are size using the minimum length. Minimum length of 180 nanometer technology is 180 nanometer, so every transistor's length are same, that is 180 nanometer, and in case of 90 nanometer technology, that is 90 nanometer, and the widths are varied according to our design requirements. So in the 180 nanometer technology, the highest size size is for MP2 and MP3, that is 800 nanometer, and for 90 nanometer technology the high size is for MP7 and MP8, that is 600 nanometer. And the performance parameters which we have discussed is the average power consumed by the proposed full adder circuit, and the delay of this proposed full adder circuit, the PDP means power delay product of this circuit, and the total transistor count in this design strategy. And we just compared to this proposed full adder with the previous design strategy. We referred to the reference previously published papers. We can clearly see by comparison this comparison table that the proposed full adder circuit are outperforming the previous works, and it is getting the better result compared to the others work in terms of average power, delay, power delay product, and transistor count. The average power, it has consumed 4.1563 microwatt, and delay is 224 picosecond, and power delay product is 0.931 fj, and transistor count is 16. And this to all these result is actually in the 180 nanometer case. And the next slide we are going to see the what is happening in the 90 nanometer technology case. So in 90 nanometer technology, uh, the same things also is happening. Also, the proposed full adder circuit is outperforming the others previous works in terms of average power, delay, power delay product, and transistor count. The proposed full adder circuit are getting 1.17664 microwatt in terms of average power, delay is 0.0913 nanosecond, power delay product is 0.107427 fj, and the transistor count is same, that is 16. And the performance analysis of the proposed full adder section, we have to focus on the calculation of the power consumption. The power consumption which are done by using this formula. Actually, the C load is the total load capacitance, that is addition of the fixed capacitance and the variable capacitance, and the power is we are taking the static power and dynamic power, and dynamic power is basically measured by using the alpha CV square F formula. And here is the elaborated form of this, and the J is denoting the actually the every nodes, and FC is the clock frequency, VDD is the power rail voltage, and the alpha is the activity factor. And in a different process technology, in case of different two different process technology, that is 180 nanometer 90 nanometer technology, the static power this circuit getting is, in case of 180 nanometer technology, the 2.139 nanowatt is the this circuit as actually consuming. And in 90 nanometer technology the static power is 0.960 nanowatt. And in the dynamic power, in terms of dynamic power, this circuit is consuming 4.1563 nanowatt in case of 180 nanometer technology design, and in case of 90 nanometer technology process variation, that is the dynamic power it is observing, it is consuming 1.17664 microwatt. A calculation of area of 1 bit adder is the main thing. Actually, the circuit is designed to minimizing the or optimizing the area of the total circuit without performance degradation, that is without losing the performance, that is the without that is consuming more power or increasing the delay. Without increasing the delay and the power, we have to minimize the area. That is the main fundamental design aspect. So to do this, we have observed that with an aim to enhance the performance of the proposed full adder in terms of power consumption and delay, the design requires strong transmission gates and weak inverters. So therefore, the channel width of transistor MP7, MP8, MN7 and MN8 involved in transmission gates, and transistor MP1, MP6, MN1 and MN6 which are involved in inverters are made relatively larger and smaller respectively. Here is the calculation of the propagational delays. Tau PDM is the main circuit delay, and the tau PDM total is the main circuit delay with adding the buffers delay. Buffers we have added to minimizing the total propagational delay, or total propagational delay. M is the number of stages of the circuits required, and C1 and C2 is the mainly the parasitic capacitance of input and output nodes respectively, and R is the linear on resistance, that is R1. And the we are using the first equation 3 and equation 4, we are getting the equation 5, which is the mainly the relation between the buffer's propagational delay and C1 C2 and the R. It is a wonderful relation that we can observe that the total number of stages required um, to design the circuit is actually directly proportional to the propagational delay of the buffer stage, and inversely proportional to the on resistance R and the C1 and C2, that is the input and output parasitic capacitance respectively. And the next section is the performance of the 32-bit full adder, which are designed by using the 1-bit full adder proposed 1-bit full adder unit. And this section will be continued by one of our fellow friends, the Korisman Pal.
Hello everyone, I am Karishman and so I will continue with the presentation. So I'll speak about the performance of 32-bit full adder. Here we see that when this 1-bit full adder is extended to a 32-bit adder, what happens? First of all, this 32-bit adder, it is implemented using a non-carry look adder as found by cascading 1-bit full adder blocks, as we can see out here. Next, buffers, they were placed after every few stages to prevent signal degradation. Also, this simulation, it was conducted at 100 megahertz frequency, and the supply voltage of 1.8 volt was used for 180 nanometer and 1.2 volt was used for 90 nanometer nodes. Next, we look at the impact of buffers. The buffers, they are required for cascading multiple adders, as otherwise it leads to delay accumulation. The delay starts increasing very rapidly and in an exponential manner, and also it leads to signal degradation. A buffer was inserted after every three stages, and this was determined mathematically, which was discussed by Sayandeep. Now look at this graph. We observe that for the 180 nanometer configuration, the unbuffered configuration, it has almost twice the delay of the buffered configuration. Whereas at the 90 nanometer level, both the buffered and the unbuffered configuration, it has similar levels of delay. Next, we talk about the power consumption analysis. Out here in this graph, we see that for the 180 nanometer level, the uh, dynamic power is much higher than the static power. This inverted dash represents the dynamic power, whereas this black section represents the static power. So we see that the dynamic power is much higher than the static power for both the buffered and the unbuffered configuration. And this can be attributed to the fact that at the 180 nanometer level, leakage current is very minimum. Whereas at the 90 nanometer level, we see that the static power starts dominating over the dynamic power. This is because of the presence of short channel effects. Specifically, there's an increase in subthreshold conduction current. Now we talk about the linearity. From this graph, we observe that from going from 1-bit full adder to the 32-bit full adder, the delay, it increases almost linearly. And this confirms us that this buffering strategy, it prevented the exponential delay growth, which is associated normally with unbuffered pass transistor logic. So to conclude, we observed in this research paper that this hybrid 1-bit full adder, it was created using a strong transmission gate and weak CMOS inverters. Then there was an improvement in power delay product of 20.56% for the 180 nanometer and 27.36% for the 90 nanometer, as compared to standard design approaches like CPL, TFA, and TGA. Further, at the end, we saw that this design was extended to a 32-bit carry propagation architecture, and buffers, they were placed after every three stages to mitigate signal degradation and to reduce the delay. So this was our main research paper that we used as our reference. Thank you.